I think it'd be really cool if Maths made a video that, like, involves some, like, real-life statistics or something like that. Like, I think it'd be really cool, like, man, yeah.
Then you better check out question 5.
Hello everybody, and welcome back to another episode of Maths. In the last episode, we looked at how we could find the probabilities of more complicated events. Basically, multiple events kind of occurring in conjunction with each other. So you could have something like the probability of one event and another event happening, or the probability of one event or another event happening. And these kind of had their own ways of calculating them. And we also saw some conditions we needed on these events in order to kind of calculate them with the methods that we were looking at. And that was independent and dependent events, as well as mutually exclusive events. So we kind of talked about all these concepts in the last video. Hopefully you found it interesting. And today we are going to be practicing those ideas to get nice and comfortable with them. So I've prepared 6 interesting problems for you, and those will be going through on the screen right now. So as always, pause the videos at these problems, try them out for yourself, and then we're going to go through them together.
Question 1.
Alright, so this first question says, identify if the events are independent or dependent. So independent events were basically 2 events that didn't influence each other's probability. They had no bearing on what the chance of the other one was. Whereas dependent events, those influenced what the probability of each other was, right? One event had an impact on the other's probability. So if we look at part A here, we're looking at the probability of rolling a 1 on a d6 and rolling a 1 on a d4. So these 2 events, they have no correlation with each other, right? I could roll a 1 on a d6, that wouldn't impact me rolling a 1 on a d4, and vice versa. So these are going to be independent events. For part B, the probability of rolling a 1 on a d6 and rolling an odd number on a d6. So maybe at a glance you might think maybe dependent just because 1 is an odd number. However, these are 2 different things that we're looking at, right? We can roll a d6 and get a 1 or not, and then we can roll another d6 and get an odd number. Whether or not we get a 1 on the first d6 doesn't impact if we get a 1 on that second d6. So these are still going to be independent events. Alright, part C, we have the probability of drawing a black marble from a bag of 10 marbles, and then drawing another black marble without putting back the previous one. So these would be dependent events because that second black marble we draw, its probability is going to be influenced based on the results of the first draw because we're not putting back the previous marble that we drew, right? So I could have drawn a black marble at the start, and now there's less black marbles in that bag to draw from. So that's going to influence the probability of that second draw. Whereas if for the first draw, we don't draw a black marble, well now there's a higher amount of black marbles compared to the other marbles in the bag. And so that has also influenced the probability. So because we haven't put back this marble, that's influencing the probability of drawing that second marble, and that means these are going to be dependent events. Right? The probability of the second one depends on what happened with the first event. And then for part D, there's an 80% chance Chad parks his car in your spot on any day, but you're too scared to confront him about it. So you park in an illegal spot when this happens. The probability of Chad being in your spot and you getting a parking ticket on any given day. So this right here, that's what we're trying to see if it's independent or dependent. So there's an 80% chance Chad parks in your spot, and then there's some sort of probability that you get a parking ticket. But the thing is, if he parks in your spot, you're going to be parking illegally, right? Because there's no other spots, so you just park in like a do not park area. And because of that, there's a much higher chance of you getting a ticket. Whereas if he doesn't park in your spot, then, well, you have your spot to park in, right? There's still maybe a small chance a mistake happens and you end up getting a ticket, but it's a much smaller chance. So it's going to largely depend on if Chad is in your spot or not. So the probability of you getting a parking ticket is going to directly depend on Chad. So because of that, these would also be dependent events. And for extra practice, try to come up with several events that are independent and several events that are dependent.
Question 2.
Alright, so question 2 says, identify if the events are mutually exclusive or not. So mutually exclusive meant basically they cannot occur at the same time. So let's go through this now. So part A, the probability of rolling an even number or a prime number on a d6. So is it possible to get both an even number and a prime number, or are these events mutually exclusive, meaning if you got an even number, there'd be no chance that you have a prime number, or if you got a prime number, there'd be no chance you had an even number as well? Well, these are not mutually exclusive because 2 is even and it's prime, right? It's actually the only even prime. And because of that, these are going to not be mutually exclusive. All right, part B. The probability you either die today or live to 130 years old. So I picked 130 because I'm pretty sure no one is 130 years old, at least not at the time of recording this. I think the world record is like 124 years old or something like that. So these are going to be mutually exclusive, right? Because if you died today, well, you didn't make it to 130. And if you made it to 130, well, because you're not 130 today, you didn't die today, right? So these have to be mutually exclusive. They can't both occur. And for part C, the probability you liked this video or subscribed because of this video. These would not be mutually exclusive because you're capable of both liking and subscribing because of this video, right? And I'm sure that's what you're going to do. All right, and for extra practice, just like with question 1, just try and come up with some events that are mutually exclusive and several that are not, just to help you really internalize what this idea actually is. Can you make examples for it? All right, let's go into the third question.
Question 3.
All right, so how many possible different meals could be made at a restaurant that has 10 drinks, 32 appetizers, 10 entrees, and 20 desserts? And assume that you're only allowed to have one of each type. So a meal consists of one drink, one appetizer, one entree, and one dessert. Well, we saw that one way we could do this was by making a tree where we literally listed out every possibility. So we'd have the 10 drinks, and then for each of those, we would have the 32 appetizers, and then for each of those, we'd have the 10 entrees, and for each of those, we'd have the 20 desserts. But that's going to be absolutely massive. We're going to have so many different possible meals here that it's just not feasible to make that diagram. So we have to kind of do the more abstract method, which was through multiplication, right? Because what we're doing is for each drink, if we could have an appetizer, we're kind of thinking of like 10 groups of these 32. But then we can also have the entree, so 10 groups of the 32 of the 10, and then we can just kind of keep going like this. So what this corresponded with was just multiplying kind of the sizes of each of these groups together. So we had 10 times 32 times 10 times 20. And 10 times 32, that is 320. 10 times 20, that is 200. So now we're looking at 320 times 200, which 32 times 2 is 64. And then we're just adding in these remaining 3 zeros. So there are 64,000 possible meals. So that would have been definitely way too much for me to draw out with that tree diagram. But thankfully we have multiplication to have our backs here. Let's go on to question 4.
Question 4.
So question 4 just is a calculate the following probabilities question. So for part A, it says find the probability of rolling a 2 or a 3 on a d6. So what's the chance of rolling a 2? There's 1 2 out of 6 possibilities, so there's a 1 in 6 chance. And the chance for rolling a 3 is also going to be the same thing, right? There's a 1 in 6 chance. And to OR these two events together, we just need to add them, right? So we have 1/6 plus 1/6, which is 2/6, which is a third. So there's a 1 in 3 chance that we roll a 2 or we roll a 3 on this d6. All right, so remember, for ORing, you just add them together, as long as they're mutually exclusive, which they are, right? Rolling a 2 is mutually exclusive to 3. All right, part B. Find the probability of drawing an ace and rolling an even number on a d6. So what's the chance of drawing an ace? Well, there are 4 aces, and the deck has 52 cards, so this simplifies to 1 in 13. So there's a 1 in 13 chance of drawing an ace. And rolling an even number on a d5, well, how many even numbers from 1 to 5 are there, right? Because this is a 5-sided dice. Well, there's 2 and there's 4, and that's it. So there are 2 even numbers out of the 5 total possibilities. So this is our probability here. And to draw this ace and to get this even number, well, to AND them, we have to multiply. So we're doing 1 in 13 times 2 and 5. Multiplying the numerators, we're going to get 2, and multiplying the denominators, we're going to get 65. And this will then be the probability of drawing an ace and getting an even number on that dice. So it's relatively unlikely, but it could happen. Who knows? And this last question, I think is pretty interesting. So you roll two d6 dice, and then you roll two more d6 dice. Okay, so in total you've rolled 4 dice. So we want to find the probability that the first pair added to 7 and that the second pair multiplied to 12. So first of all, let's figure out the probability of these events by themselves, and then we're going to combine them together with this and, right? So what's the probability that a pair of dice adds to 7? Now you might think that's kind of a complicated idea, right? I mean, we know you could get a 1 and a 6, or you could get a 2 and a 5, but it seems like there's several options. It's not just something we can immediately guess. So the best way to do this is to write out all the possibilities, and a really nice way of doing that is to make a little table. So I'm going to list out all the numbers here from 1 through 6, right? It's a d6. And then all I'm going to do is I'm just going to add them, right? So 1 plus 1 is 2, 1 plus 2 is 3, and so on and so forth. All right, so this is what we get for all the sums, right? For example, 3 plus 4, if we go to where those line up, we get a 7, right? Since 3 plus 4 is 7. So this table tells us all of the possible sums, and we see that if we kind of look at the diagonals, in particular this diagonal right here, we're going to get all of our possibilities for getting a 7, which is quite a lot actually, right? So we could either get a 6 on the first dice and a 1 on the second dice, or a 5 on the first dice, a 2 on the second dice, and so on and so forth. So in total, there are 1, 2, 3, 4, 5, 6 of these outcomes that give us a sum of 7. And the total possible outcomes, well, we're doing 6 times 6, right? So there are 36 possible outcomes. So 6 out of 36, which simplifies to 1 in 6. So there's a 1 in 6 chance that the first pair of dice sums up to 7. All right, and then for the second pair multiplying to 12, we can do the same kind of thing. We'll just make another table, but instead we'll just multiply the numbers this time. All right, so how many multiply to 12? Well, let's see here. We've got 1 12, 2 12s, 3 12s, and 4 12s in total by the looks of it. And once again, there are 36 outcomes here. So there's a 4 in 36 chance that the product of our dice in the second pair of dice is going to multiply to 12. And this simplifies down to 1 in 9. All right, so we have a 1 in 6 chance and a 1 in 9 chance, and we want and, right? So the probability that the first pair adds to 7 and the second pair adds to 12. So what that means is we just multiply these two events. So 1 in 6 multiplied by 1 in 9, and that gives us 1 in 54. So there's a 1 in 54 chance both of these things happen. And for extra practice, just come up with two different probability events and figure out the probability of the first and the second, and then also come up with some probability events and figure out the probability of the first or the second. For the first and the second, make sure that these are independent events, and for the first or the second, make sure that these are mutually exclusive events.
Question 5.
All right, so the attached table is the number of births in each month of the years 2018 to 2022 in Canada. I got this off of Statistics Canada. I should have the link in the description as well as on the screen right here. So you can also kind of look at this table for yourself. So I have a few questions kind of using this table. First off, which year was the most likely to be born in? Okay, well, all we need to do is we need to look at what year had the most number of births. So we're looking at like 2018 has the most births, right? 374,617 is bigger than all of these other years, so it is most likely to have been born in 2018 by the looks of it. And which was the least likely to be born in? Well, what has the least amount of births? And that's looking like 2022, right? With 351,679 births being less than all of these other total number of births here. And it actually wants us to figure out the probability of these. So we have the total amount of births for those years. And what's the total amount of births that we're doing this out of, right? The total amount of possible outcomes. Well, that is going to be just the sum of all of these births over these 5 years, right? Because if we add that up, that's basically telling us how many babies were born during those years. And then these are the outcomes for those babies born in 2018, or this is how many of those babies were born in 2022. So that's going to give us our probabilities. So let's add up all these numbers. So the total amount of births is looking like 1,830,230. So then the probability to be born in 2018, well, that's going to be this 374,617 out of this total we just calculated, which is 1,830,230, which when I do that division and I multiply by 100 for the percent, right, it's going to give me roughly 20.47% chance that you were born in 2018. And the probability you were born in 2022, we're just going to do 351,679, right? That's how many were born in 2022, divided by the total, and then multiplying by 100% to get our percent, we get approximately 19.22%. So there's a 19.22% chance that you were born in 2022. So honestly, not that much worse than the chance of being born in 2018. So despite there being around 23,000 more births in 2018, because we're working with just such an astronomical amount of people here, that relatively large difference isn't actually that large as we see it being reflected in these percentages here, not being too different from each other. Okay, so that was part A. Now if we go back to look at what part B is, this says out of the babies born in 2022, what was the probability of being born in September or October? All right, so it's saying out of the babies in 2022. So that means our total now isn't going to be everything here. It's not going to be the 1.8 million or whatever it was. It's now going to be just the 351,679 because the question explicitly says out of the babies born in 2022. All right, so our total then that we're working with is going to be 351,679. And it's saying what's the probability they were born in either September or October. So to be born in September, that's 30,472 births. And to be born in October, that's just the month after, that's 29,671 births. So then to be born in one or the other, we just add them, right? So we get 30,472 plus 29,671. And to get the probability, we're going to have to divide by the total amount of births in 2022. So 30,472 plus 29,671, that is going to be 60,143. And then if we divide that by 351,679 and multiply it by 100 to get our percent, we're looking at roughly 17.1% of babies in 2022 were going to be born in September or October. Part C says out of the babies born between 2018 and 2022, what was the probability of being born in September or October? So now what we're doing is the total is all of the babies between 2018 and 2022. So that goes back to our 1.8 million value that we had. And it wants to know what's the probability of being born in September or October. So now it's not just these values we have to consider, it's all of the September babies over these years and all of the October babies over these years. So what we're going to have to do is we're going to have to add up all of these 10 values here for each of the September and October babies for those years, and then divide that by the total, right? Because this is all of the outcomes that actually match what we're looking for, right? September or October. And the total is just, well, all of the babies, right? The 1.8 million. All right, so I'm just going to plug these into my calculator, add it all up, because these are all of the possibilities that they were born in there, right? So it's just adding it all up, right? This or that, or that, or that, or that, etc. Those contribute to this probability, so we just add it all up because they're or, right? All right, so I end up getting 313,526, and the total amount of babies born in those years, we calculated previously, was 1,830,230 babies. So that means that the probability over these years that you would have been born either in September or October is going to be 313,526 divided by 1,830,230. Multiplying by 100 to get our percent, we're going to get approximately 17.13%. So extremely close to the percent that we got for the September and October babies for the year of 2022. So that's kind of interesting. All right, and let's look at the very last part for this question. Your friend has two kids. One was born in 2020 and the other was born in 2022. So what was the probability that the eldest was born in May, so that's in 2020, and the youngest was born in February? All right, so let's figure out the probability of these individually, and then we're going to add them together through multiplication. All right, so for the eldest, that's the one born in 2020, what's the chance that they were born in May? Well, we just need to figure out how many babies were born in May. So for 2020, right, we need to figure out how many babies were born in May. So that's 31,320 babies that were born in May, out of the total, which was 360,801 babies. All right, so that's going to be the probability that they were born in May. And then the other baby, which was born in 2022, what's the chance that they were born in February? So 2022 is right there, and the chance that they were born in February is right here. So that is going to be 26,246 possibilities or outcomes that were in February, out of the total possibilities in 2022, which were 351,679 different babies. So that was the probability that they were born in February. All right, so now to combine these, we're just going to have to multiply them, right? Because it's the probability the eldest was born in May and the youngest was born in February. So we just have to multiply these to combine with and. So we do 31,320 divided by 360,801. And then I'm going to multiply that by 26,246 divided by 351,679. And if I multiply that by 100 to get my answer as a percent, we're going to get 0.65% chance. So it's not super likely that the baby born in 2020 was in May and the baby born in 2022 was in February. It's actually relatively unlikely for that to have occurred, which is kind of interesting.
Concluding thoughts.
All right, well, that's going to do it for me today. I hope you found this video interesting. Thank you so much for watching, as usual. I'm looking forward to the next one where we're going to get to that Minecraft application, so you better be anticipating that one as much as I am. But until then, you have yourself a great day, you stay groovy, and I'll see you in that next video.
F.O.A. math.